Hi everyone. Thank you so much for joining us today on our session for Reading Asia at Professor for AI. We have with us a very special guest speaker, Hongyu Wang. Hongyu is a second year Ph.D. student at VIPL Group, Chinese Academy of Sciences, under the supervision of Professor Xilin Chen and Professor Ruiping Wang. He completed his B. Engineering degree from Department of Computer Sciences and Technology, University of Science and Technology of China. He was a research intern at Microsoft Research Asia from August 2021 to January 2023, and his research interests are on the efficient architecture for large-scale foundation modeling and multimodal reasoning. This session is on BitNet, which is a very famous uh, neural network for which is a new way for training large language models in 1 bit. Thank you so much for joining us, and I'll pass it over to you.
Thank you so much for inviting me to join this talk. Let me share my screen. Can you see my screen now?
Yes, you can see.
Yes. Thank you again for inviting me to give this talk at Cohere for AI. I'm very appreciated to have this opportunity to share our latest progress on 1-bit large language models. I'm Hongyu Wang, a second-year PhD candidate from VIPL Group, Chinese Academy of Science. And in this talk, I will present 3 papers starting from BitNet B1 we released last year to BitNet B1.58 and its training tips we released this year. Let's get started with BitNet B1 first. This work was done during my internship in the Microsoft Research Asia with my mentor Shuming. Recent years, we have all witnessed a trend towards large-scale foundation models. The parameters of these large language models vary from billions to trillions. And hosting this large language model is very expensive, and the increasing model size poses significant challenges for the deployment of these large language models. As the model size grows, the memory bandwidth required for transferring the model parameters from DRAM to an on-chip accelerator, for example, SRAM, becomes a major bottleneck. Therefore, the inference of large language model is mainly memory bound. But fortunately, despite this large language model has a large amount of parameters, these large language models are extremely sparse, and many techniques are developed to utilize the sparsity of large language model to improve their inference efficiency. For example, pruning, mixture of experts or MOE, and model quantization. In these 2 works, we focus on model quantization, which aims to compress the bits of each parameters. For example, we can compress the IP16 weight IP16 model to int8 without compromising the performance, but it can save 50% of the memory consumption. Most quantization methods nowadays are for large language models are post-training, for example, GDQ and AWQ. These methods are widely adopted for the deployment of the large language models, especially for on edge devices. This post-training quantization do not introduce extra training cost, since it does not require to retrain the whole model, but actually try to compress a high precision model into a lower precision after the training. But empirically, we find that this post-training quantization do not work well on ultra-low precision models, especially lower than 2-bit. Therefore, in this work, we focus on quantization-aware training and try to explore the scaling law of 1-bit large language models in these two works. We propose BitNet B1 in this paper, which is the first 1-bit transformer for large language models. BitNet B, especially we introduce bit linear as a drop-in replacement of your n-point linear in your PyTorch code to train 1-bit weight from the scratch. For the weight quantization, we first zero min the latent weight and then apply the sign for each parameters. This quantization is also widely adopted for the training of binary convolutional neural network. As for activation, since these activations usually have too many outliers and are more sensitive to the performance, to the quantization. Therefore, in this work, we use ABS max to quantize the activations to int8. As for the training of BitNet, we adopt several techniques to make the BitNet training work. For example, we adopt ST estimator to conduct gradient estimation. And during the training, we conduct the mixed procession training and maintain a latent weight accumulate parameter updates. Let me give you an example. Actually, during the training, we do not perform the real 1-bit weight matrix multiplication between a 1-bit weight and 8-bit activations. Instead, we adopt a schedule quantization during the training. As shown in this figure, we first maintain a high procession weight to accumulate parameter updates. This weight is 50 FP16. And during the forward of the training, we will first quantize the latent weight into a binary weight and a high procession scaling factor. Then we will immediately do the dequantization, and which is the same for the activations. But during the inference, we can first offline quantize the weight into binary weight and a high procession scaling. Then we can first conduct a matrix multiplication between the binary weight and int8 activations using the customized kernel, and then element-wise apply the scaling. Since our weight is per tensor quantized and the activations are per token quantized, so the training, the computation of training and inference is equal. As for since the quantization has many operations such as sine and round, these operations are not differentiable. Therefore, we adopt ST estimator to directly bypass these gradients of weight and activations. As for the training hyperparameters, we found that a large learning rate is very critical to the optimization of BitNet. In our experiment, we found that BitNet is much more stable than IP16 large language model. I think this is maybe because that we constrain the magnitude of the weight through binary quantization. Then we find that BitNet actually can tolerate and benefit from a much larger learning rate compared with a standard IP16 large language model. Then we estimate the energy cost of the BitNet and the IP16 large language model according to an energy model released in B.Eng paper. The energy cost is defined as the sum of energy introduced by each type of operations. And we find that during the matrix multiplication, the energy cost of IP16 multiplication between elements is a major bottleneck for IP16 large language models. And for example, given a shape of n times n weight and a shape of n times 1 input x, we find that the number of IP16 multiplication in IP16 large language model is n squared. But since our weight is 1 bit, therefore we can fully transform the standard floating multiply then add in matrix multiplication into fully int addition, which save a large amount of floating operations in BitNet. Therefore, we estimate the expected energy cost of BitNet and the IP16 large language model across different scales. And as shown in this figure, we find that the energy cost reduction ratio increase as the model size grows. It indicates that a very promising direction to utilize the 1-bit weight, 8-bit activations to design an environmental friendly hardware for the deployment of large language models. Then we try to investigate whether 1-bit large language models have a similar scaling law like the widely adopted IP16 large language models. Our answer is yes. And to ensure a fair comparison, we train a series of BitNet and IP16 large language model of different with the same amount of 10 billion tokens across different scales. We find that the validation loss decrease as the model size grows. And we also find that the performance of BitNet is very predictable and satisfy a power law similar to IP16 large language model. Therefore, in this paper, we use the valid loss of 125 million to 2.7 billion BitNet to accurately predict the validation loss of 13 billion and 30 billion BitNet. Then more importantly, we actually find that BitNet has a much better scaling law compared with IP16 large language models. As shown in this figure, we find that at a very small scale, for example, 125 million parameters, IP16 large language model is still far better than BitNet. It has a lower validation loss of 1.5 on the test set. And but if we scale the parameters to 100 billion, we find that the gap between 1-bit BitNet and IP16 large language model will continuously narrow to less than 0.1. That means if we try to train a very large language model, even with trillions of parameters, then 1-bit BitNet can achieve the same performance compared with a standard IP16 large language model. But at the same time, BitNet actually has a much better inference efficiency compared with IP16 large language model. Therefore, in this paper, we propose inference optimal scaling law. The axis is the expected energy cost estimated by the energy model, and the y-axis shows validation loss. And we find that, as shown in this figure, BitNet achieves lower validation loss compared with IP16 large language model, given the same amount of inference energy budget. And even 30 billion BitNet had the similar energy cost than 760 million IP16 large language models. Then we compare BitNet with several state-of-the-art post-training quantization method and IP16 baselines on their valid perplexity and zero-shot accuracy on inner tasks. As shown in this table, we find that BitNet has competitive performance compared with IP16 large language models, and shows a better performance than this SOTA post-training quantization method on the ultra-low bit models. We also conduct the comparison on 1 billion and 3 billion scales, and we find that this gain is consistent across different scales. After that, we present BitNet B1.58 in this year, and this is the first ternary large language model that can match IP16 large language model given the same amount of training tokens. This work was also done during my internship in Microsoft Research Asia, and with my mentor Shuming. First, let's revisit the scaling law of BitNet B1. The advantage of BitNet B1 is that we actually find a better scaling law. That is, as the model size grows, the gap between 1 bit and a quantized model and the IP16 large language model will continuously narrow. But unfortunately, BitNet B1 may require a much larger size, even larger than 100 billion parameters to fully match IP16 large language models, which is beyond our computation budget. Therefore, in this paper, we try to answer the questions, does 1 bit large language model can match IP16 large language model at a smaller size? Our answer is yes. Actually, we adopt several techniques to achieve this target. For example, group quantization and combining 1 bit BitNet B1 with a mixture of experts. But at the end, we find that simply adding a zero can significantly improve the performance of BitNet B1. Therefore, in this paper, we introduced BitNet B1.58. And for BitNet B1.58 also inherits many design choices from BitNet B1. First, it also adopts sublayer norm to stabilize the training of the quantized model. And for the weight quantization, we adopt ABS min function to quantize each parameter to ternary values, that is -1, 0, and 1, instead of quantize these parameters to binary in BitNet B1. As for activation quantization, in this paper, we adopt symmetric ABS max to per token quantize the input to int8. The symmetric design, the symmetric ABS max is more friendly for the systematic optimization. Actually, we find many interesting results during the training of ternary weight. First, as we all know, the training loss curve of standard IP16 large language model generally shows an exponential decay. But during the training of BitNet B1.58, we find that it behaves like a S-shaped pattern. As shown in this figure, we find that the training loss will suddenly decrease at the end of the training. And we also find that this choice is closely related to our choice S-shape is closely related to our choice of weight decay. And when disabling weight decay, this S-shape pattern will disappear. But this choice has slightly worse perplexity than enabling weight decay as 0.1. Therefore, despite this S-shape pattern significantly improves the overall performance, but it also makes us more difficult to predict the final performance according to the training loss during the process. Therefore, to make the whole training process more predictable, we adopt a two-stage training recipe. For the first half of the training, we use a very large learning rate and enabling weight decay to make the model converge as faster as possible. And then for the second half of the training, we try to lower the learning rate and disabling the weight decay. With this two-stage training recipe, we can successfully remove the significant loss reduction at the end of the training to the half of the training. Besides, we also find that the training tokens also plays an important role for this S-shape pattern. If you train BitNet with less tokens, for example, less than 1 billion tokens, we also empirically find that it does not behave like a S-shaped pattern. So this pattern is also very interesting, and I think there are much room for the training optimization for ternary large language models. Then, similar to the BitNet B1, we conduct a series experiments to explore the scaling law of BitNet B1.58. And we find that BitNet B1.58 also satisfies the basic scaling law of BitNet B1. That is, as the model size grows, the gap between a quantized model 1.58 bit and IP16 large language model will continuously narrows. As shown in this figure, the training law, the gap between IP16 large language model and BitNet will continuously narrows, and as we scale the model parameters from large scales, 700 million parameters to 3 billion parameters. And furthermore, we evaluate their validation perplexity on the Wikitext2 and C4. And we find that as the model size reaches 3 billion parameters, BitNet B1.58 can match IP16 large language model with the same amount of training tokens and parameters. And furthermore, we also evaluate their the zero-shot accuracy of these models on a range of end tasks. And the conclusion is also consistent that we observed during the validation perplexity experiments, that BitNet B1.58 can match IP16 large language model with 3 billion parameters and 100 billion training tokens. Then we measure the inference cost of BitNet B1.58. Currently, we still implement this inference process with an int8 times int2 kernel on A100 cards, compared with 70 billion IP16 llama. BitNet B1.58 is faster and smaller. It can achieve 4 times decoding latency, but only use 40% memory consumption, as showing these two figures. And we also, since our model is much smaller than IP16 baselines, therefore BitNet B1.58 can use 11 times larger maximum batch size, which can lead to 9 times larger throughput. Therefore, BitNet actually defines a new scaling law as for the model performance and the inference cost. We list some equations there, and we find that 70 billion BitNet B1.58 is even more efficient than 30 billion IP16 large language models, which bring us a huge potential to the deployment of large language model on many edge devices. For example, your PC and your phones. Then to examine whether BitNet is also friendly for scaling with more data, we train a 3 billion BitNet with 2T tokens and compare with a strong baseline stable LM 3 billion and compare its results on 2T tokens. We find that BitNet B1.58 has slightly better performance, 1% gain of average scores on these benchmarks. This also verifies the effectiveness of BitNet B1.58. Then we also conduct many experiments to explore the activation quantization and the KV quantization of BitNet B1.58. We find that if we compress the weight to 1 bit and the activations to 8 bit, we can losslessly to compress KV cache into 4 bit with, as shown in this figure, BitNet with a 4 bit KV cache can achieve minimum accuracy loss compared with the baseline. And as for activation quantization, we find that the activation before down projection in feed-forward network has many outliers and actually are more difficult to be quantized. Therefore, we find a hybrid quantization recipe is very useful in our experiment. That is 1 bit weight, 4 bit activations, and 8 bit down projections. It has a negligible accuracy loss. Then in these few weeks, we conduct many experiments on BitNet B1.58. And first, we scaled BitNet to a larger scale, a larger model size, larger than 7 billion, and try to integrate BitNet with a mixture of experts. We find that BitNet works perfectly on these settings, and I hope we can release these results in the next few months. And I'm also excited to see that the community have much more discussion since we released the BitNet B1.58 paper, and a team from Hugging Face from community have already successfully reproduced and open sourced the BitNet with 100 billion tokens as presented in the paper. Despite the train a small amount of training tokens, I think it's a very good start. It's maybe a good start to conduct some systematic optimizations for this ternary weight and 8-bit activations large language models. Then we released a paper named "The Era of 1-Bit Large Language Model: Training Tips, Code, and FAQ" to answer some questions from the Hugging Face daily papers. And I think some questions you might feel very interesting, and I list in these talks. And the first, some people ask why we train BitNet B1.58 from the scratch. How about continue training a full procession or half procession model, or conduct knowledge distillation? First, as for continued training, we found that actually current post-quantization method for these ultra-low precision models generally adopt group quantization, which is very difficult to for system for continued training or fine-tuning or some optimization. Instead, we also try to using the standard scalar 1.1 bit quantization for IP16 large language model. And we find that this approach will completely broken the model, thus has a similar performance to train the model from the scratch. That means if we trying to first compress a 7 billion llama into 1 bit and then conduct continued training, it has minimized the difference between two with directly training a randomly initialized model from the scratch. Then as for the knowledge distillation, we also tried many distillations methods before. For example, we tried to use soft logic distillation and try to use a large language model to generate some data to then to continue training these models. And we find that the gap between this method and IP16 baselines is still quite large. So we do not apply knowledge distillations in this work, and our target is to explore the scaling law of 1 bit and 1.58 bit large language model scale, the scaling law. Then some people ask why we choose -1 as the binary weight in BitNet B1. How about 0 1 of binary weight? We actually test this possibility, and we empirically find that 0 1 of binary weight is very unstable during the training. I think this may be this is because that actually the weight, the magnitude of the weight is much uniform, and if we choose 0 1, it means that we actually will create a lot of outliers for the weight quantization. This may not be friendly for estimators. Therefore, this training is very unstable. Then some people ask the distribution of the ternary weight of pre-trained models. We find that the distribution is nearly uniform, and of course we can control the scaling in the ABS mean function of weight quantization to enlarge the proportion of 0. But empirically we find it will hurt the overall performance. Here are my takeaways for these talks. In conclusions, we find that BitNet has a better scaling law compared with IP16 large language models. That is, as the model size grows, the gap between a quantized model, for example, 1 bit, and or 1.58 bit, and IP16 large language models will continuously narrows. And more importantly, BitNet B1.58 can match IP16 large language model with 3 billion parameters and 100 billion training tokens. So feel free to scale BitNet to a larger size. And then we find and BitNet defines a new scaling law. As for the model performance and inference cost, that 70 billion BitNet B1.58 is more efficient than 30 billion IP16 llama in terms of latency, memory, and energy cost. I also put the QR codes of these three papers I mentioned in this talk in this page. If you have more, if you are interested in BitNet and the quantization aware training, you can see more results in these three papers. And thank you again. Thanks for this opportunity to present these talks. And if you have any questions, feel free to ask me. Thank you again.
You can unmute and ask the question. There is a question in chat as well.
Let's see the chat bot.
In the end of chat.
Currently, we only adopt model quantization for BitNet here. So we do not explore the pruning techniques. But actually, we did some interesting work in these weeks, and maybe you can find some. You can stay tuned. We will update some interesting results. Maybe released to the training. Release about the pruning of BitNet B 1.58.
Will this be released on archive or?
Actually, it is. We put the third paper. That's the error of 1-bit large language model training tips, code, and FAQ in our GitHub. So you can see, you can use the QR code I listed before.
Yeah, I got got the message, but I was thinking about the next work that you alluded to, which has some sort of pruning applied. Do you think you can make that available to us in the coming weeks, or is it on the back burner?
It's also a backbone, and sorry, I can't talk too much right now. But I can. But it's similar to the pruning, but it's more. It's also a update version of BitNet B 1.58. But I can mention that if we compress, actually, the inference of BitNet B 1.58 is not memory bound. It's actually compute bound. So we will put more efforts to accelerate the computation during for the future optimization of BitNet B 1.58.
Cool, thanks.
Why not opt parallel training on clusters? Actually, we conduct model parallel during the training of BitNet, especially for larger scale models, for example, 7 billion and 13 billion models. And the training of BitNet B 1.58 is basically same as we train a standard IP16 large language model. We only modify the forward computation of each linear projection. Uh, what about the training infrastructure look? Let's say 3 billion models. Currently, we adopt H100 cluster, and since we cannot train, we're still doing a lot of experiments. For these models, we actually train 3 billion models with 100 billion tokens on the clusters with nearly 3 days, 3 days or 2 days. Have you tried experiments on self-supervised fine-tuning for 1-bit model? Actually, my mentor tried some experiments on SFT for BitNet, and we find that it also works perfectly. And we also try to scale BitNet to more training tokens at 3B scale, hoping this model can be updated in the next few months. If I remember correctly. Oh, yes, I think ABS mean quantization function is used for activation function. Yes, but we find that ABS max function for 8-bit quantization is more has more better performance compared with ABS mean function. And some modification of ABS mean function introduce a learnable variable, a learnable parameters, and it will lead to some unstable training especially during the pre-training process. Therefore, we choose unparameterized ABS max function for at this moment. But I think it will be the ABS mean function may be more useful if we try to train, for example, a 1-bit a truly 1-bit weight and a 1-bit activation models.
Have any other question? I think we can conclude the session here. Thank you so much, Hongyu, for your time. It was really an amazing session.